Now we're going to discuss a very powerful analytical tool called nuclear magnetic resonance, or NMR. And while there's many different types of NMRs that we could learn, we're going to start off with the one that's most important for this course, and that's called proton NMR. So proton NMR is an instrumental method that is going to allow us to identify and distinguish protons, okay, in slightly different electronic environments, okay? We're going to use magnetic fields to actually generate magnetic fields around these atoms and see what the strength of the magnetic fields are that we get back from them. Okay? Now, I'm actually going to leave the entire scientific explanation of how nuclear magnetic resonance works up to your professor or up to YouTube, because you could definitely spend a good 10-15 minutes learning all about that, and that's not really the most important part. What I'm going to really focus on is how to read it, how to understand it, and what you need to know to pass your exam, right? That's what we do here. So let's go ahead and jump right into what the spectrum looks like. As you see, this spectrum has units that you have to get familiar with. It has shapes that you have to get familiar with. Let's just talk about the basics in terms of navigating the spectrum. Well, first of all, we're going to see that on the x-axis, we have this unit of ppm, okay? ppm stands for parts per million, and it's really just an arbitrary unit of measurement that we use for this. Just some scientist decided that he wanted to measure the magnetic response of these atoms or these nuclei through parts per million. So that's what we go with, okay? Notice that it starts at 0, and it usually goes up to, here I have it about to 11. It actually usually ends around 13, okay? So 13, 14, somewhere around there, you're going to get your entire spectrum, okay? Now notice that we have these words at the top that are kind of our navigation words, okay? And it's important that you are able to associate these. So first of all, we have the words downfield and upfield. Notice that upfield is close to 0, and downfield is close to the high number of 13, okay? Now this might make sense while I'm telling you right now, but you'd be surprised once you shut off this video how confusing that could be. It's like upfield, is that towards the bigger number or the smaller number? So we have to figure out a way to memorize that, because I want you to make sure that you have that for the rest of your life, you know? Kind of a life-changing definition. So let's talk about something else, which is shielded and de-shielded. So shielded is a word that we're going to discuss in a second. De-shielded would be the opposite of that word, correct? Okay? So I'm going to define what it means to be shielded in a second. But notice that downfield and de-shielded happen to be the same direction of the spectrum. So if you say something's downfield, that's the same thing as saying it's de-shielded. If you say it's upfield, that's the same thing as saying it's shielded. So the way I like to remember this is, I'm sorry, I'm a guy, double D's, all right? So you got your downfield, you got your de-shielded, super inappropriate, and it worked. Now you're going to remember that, okay? So now you know, kind of, if you can remember which direction they go, then you're fine. You got everything else, okay? So let's go ahead and talk about just some general features of the NMR spectrum. Well, first of all, there actually is no natural zero for an NMR spectrum. The zero is basically going to be a molecule that is our test molecule that we run all of the other molecules against. And that test molecule, the one that we use as our zero, is going to be called TMS. Okay? That stands for tetramethylsilane, okay? It's basically a silicon molecule that has 4 methyl groups around it, okay? And that happens to be, remember that we said 0 is around shielded? That happens to be an extremely shielded molecule. And we'll discuss what that means. So basically, electrons are what shield protons from the effects of NMR, okay? So basically, what that means is that the more electrons that I can have around my hydrogen, the less it's going to experience the magnetic field that I'm producing from the NMR, okay? So the more electrons, the less it experiences it, the more shielded it is. The more stripped of electrons it is, the less electrons it has, the more it's going to feel that magnetic field, and it's going to actually result as a consequence of that. and the more downfield or D-shielded it's going to be, okay? So one way you can think of it is that the further downfield your proton is, the more super inappropriate, the more naked the proton is, okay? So you're going in the direction of your double Ds, now you're naked. I don't even know where this is going. I didn't even plan that, by the way. But basically, what I'm trying to say here is, imagine that you're going out into the middle of like a Michigan winter or something like that, right? It's bitter cold. You have a big wool coat, you're not going to really feel the cold that much, right? So that would be the idea of being shielded. You're not going to feel that cold, so you would kind of show up in this shielded area, kind of like the tetramethylsilane. It's very shielded. It's got all these methyl groups, right? But if all of a sudden I were to take off that big wool coat and all I have is boxers on, okay, so I've given you a great visual now, I'm going to feel super cold, and I'm going to result much more downfield or D-shielded, okay? So in general, the less electrons I have around me, or the thinner my coat is, the more downfield I'm going to result, okay? So now we understand kind of the shifting of the right to left idea here, but it turns out that there's a lot more information that we can gain than just that. There's actually 4 different types of information that we get from an NMR, from a proton NMR spectra, and we're going to kind of introduce what those 4 types of information are, okay? So the first type of information that we're going to be able to learn is we're going to learn the number of signals, the total number of signals. And the total number of signals is then going to describe how many different types of hydrogens are present. Because basically, if you have, let's say that you have 3 different peaks, or let's look at our example here. This one has 4 different peaks. Notice that it has peak A, peak B, peak C, and peak D. Okay, or signal A through D, right? All of these protons are wearing different layers of clothing. You could imagine that proton A is the guy with the big heavy jacket, and proton D is the one that he's in the process of stripping down, okay? So, and the other guys are somewhere in between. So what that's telling us is that we have 4 distinct types of protons on this molecule. Just by telling me that, that's already a lot of information, okay? So it tells me how many different types of hydrogens or protons are present, okay? Then we've got the chemical shift, okay? The chemical shift is the actual part that's the parts per million. That's going to tell me how shielded or de-shielded the actual protons are. So now I'm going to know that there's 4 different types of protons, and this one has a shift of 4, this one has a shift of 2. That's going to tell me kind of what kind of functional groups they're attached to. See where we're going with this? It's already telling me a lot of information. But there's more than that. We're also going to be able to use the height of the signal. So it turns out that on this sample NMR that I showed you, notice that some of them are really short and some of them are really tall. That's actually for a reason. It turns out that the ones that are taller are the ones that take up more area under that curve. That's going to represent that there's actually more of that type of hydrogen, okay? So just for example, taking A versus B, okay, notice that I have A and B next to each other. I could safely say that there's more of the coated hydrogens, the wool coat, than the ones that are B, the ones that have a slightly less clothing on, or that are slightly more de-shielded, because there seems to be a lot more area underneath that curve than there is below B. Get what I'm saying? So it turns out that we call that the relative ratio of hydrogen. So basically it tells us that we have more of one type of hydrogen and less of another. Again, that's a lot of information. But finally, we have spin splitting, or what's called multiplicity. And spin splitting is that final piece of information that really just helps us determine the structure of a molecule. And what it does is it describes to us how close or how far the different molecules are from each other. Now, spin splitting is represented by the fact that instead of just being one peak, notice that a lot of these have like multiple little peaks in them. For example, D, the guy that's most stripped down, appears to have 4 little tiny peaks in it. Those are what we call the multiplicity or the splits. And that's going to tell us what type of hydrogens he's next to, okay? So, tons of information here. What we're going to do now is we're going to spend lots of time going through every single piece of this so that you really understand. We're going to do every single piece of this in depth so that you can take one of these NMR spectra and understand perfectly what's going on. Okay, at least that's the goal. So let's go ahead and move on to the next topic.